Good afternoon to all the viewers of this program. I am Hitendra Padalia. I am with Forestry and Ecology Department of IIRS. And today I will be talking about the polarimetric SAR remote sensing applications in forestry. As you are aware that forestry is one of the area where we have a lot of expectation from application of SAR remote sensing or polarimetric SAR data applications. The outline of my presentation is like this. Briefly, I will be talking about the polarimetric SAR data, and then I will be coming to how it for different polarization interacts with the vegetation canopies, and then I will be talking about the various applications which are possible with the SAR data with focus on polarimetry. So as I told that in forestry, we basically require SAR data mainly for two purposes. One could be the mapping or detecting the changes which happens in the forest areas due to disturbance. And secondly, we are interested in determining the stocks of carbon or biomass, particularly in the areas which are affected by the cloud. For example, tropical forest areas, we require SAR data observations. And globally also there are a lot of initiatives nowadays. One very important initiative is GFOI, Global Forest Observation Initiative under CEOS. CEOS is a Committee on Earth Observation Satellite. So under GFOI, there is an emphasis on use of SAR data in conjunction with optical data for improved forest resource inventory, and also particularly for UN program REDD, reduced emission from degradation and deforestation. There also we have a lot of potential of applying SAR data. Now, if you look at this particular slide, so this shows the sensitivity of different wavelength of microwave energy or X, C, L, P, and their sensitivity to different components of forest tree canopy. And you can see that the wavelength size of these bands is different. They are in centimeters, so they are sensitive to different component of canopy, for example leaf, small twigs, branches, trunk. And on the other hand, optical remote sensing is mainly gives you the surface information, and whereas SAR data has applications particularly for biomass carbon inventory because it can penetrate the forest canopy. With respect to polarization, as you are aware that different polarizations are available, like polarization and cross polarizations are available, and it has been seen that the forest responds differently in different polarization. For example, if you see the forest canopy here, that and then interaction of different wavelength, so you find that shorter wavelengths like X and C, they mostly get scattered from the top of the canopy, and whereas the L and P band can penetrate the foliage and can interact with the branches and trunk, and so this way they bring different information about the forest canopy. And then you see one image with the different colors, green, blue, and green areas are basically represented by forest. So if you have for example a data SAR data where polarization HS, HV, VV are there, then you will find that vegetations is scattering, in particularly HV polarizations gives a distinct scattering for the forest areas, and this is the basis how we can use the different polarization for classification of SAR data and differentiating forest from other land cover categories. Then With respect to incidence angle, this is, that also matters, because with incidence angle, the information about the target, for example, forestry target also varies. And you can see with this example that there are incidence angles. As incidence angle varies, there is a difference in terms of scattering in the image. So it also depends on incidence angle, what type of scattering you are getting. You know that broadly in the image, you have volume scattering over forest canopy areas, double bounce scattering, as well as odd bounce or single bounce scattering from the non-vegetated areas. And this may vary, but if you actually change the incidence angle. Similarly, in the forest areas, as you know, there are seasonal changes happens in terms of, like, this is an example of deciduous forest in central India. And so you will find that a lot of changes happens in the forest area, and that are these changes also changes the backscatter properties in the images of the image, and that's why they appear different in different seasons. So one should have idea of the phenology of the vegetation while mm, understanding the signature of a SAR image. uh, Another thing is that now we are getting fully polarimetric data, like this one is a radar set quad pol data where all polarizations, four polarizations are there. And this data is very rich in information content. And for example, here you can see that this is a plantation area, and after applying a decomposition, this image can be seen in different colors. And these are different types of plantation in that area. And as well as outside agriculture area also, you see that agriculture field with different color representing different type of scattering. So this single image can be very useful for broad classification of different land use, land cover category in a particular area. So the polarimetry here is playing a very important role. Earlier, we used to have only data available in single polarization like HH, HV, VH, VV polarization, but now all these polarization are coming in one data sets, and this is useful for doing a polarimetric analysis. Then globally, now we have been able to do forest cover change mapping using the polarimetry information, and particularly with the allows 2 data which is available since 2006. So globally, this HV polarization images have been used, and to differentiate the tree cover areas from non-tree areas. And this way, the global forest cover maps has been prepared for different time period, and the change areas has been brought out. So uh, so there is a role of HV polarization here in differentiating tree from non-tree areas. Another application could be, though we don't expect that we will be doing very good classification of forest type based on SAR data, because SAR data gives you mainly structural information. You also need information about the pigments and other characteristics of plant that is not available in SAR data. But SAR data can be used in conjunction with optical data for improving the classification accuracy. And there are several techniques are nowadays available which can handle the high dimensionality SAR data. Technique like support vector machine, artificial neural network, random forest. So these are the techniques which can use a number of SAR variables derived from quad pol data, and can be used for classification of forest types or other land use, associated land use categories. Then Another applications which is not possible with the single single polarized SAR image also. For example, if you take HH intensity, HV images, and then you apply certain textual indices, and such textual indices are available in the routine the softwares which we use, for example, RADAS and NV software. And these textual indices, for example, gray label co-occurrence matrix. So there are different textual index, variance, covariance. So these indices you can apply on image and then see how they can be helpful in differentiating different type of land feature. For example, in this image, one homogeneity texture has been applied, and you can see that this texture is useful in differentiating the water body and from the rest of the area. Similarly, the forest areas, dense forest areas appear distinct from the agriculture outside agriculture area. So the point is that SAR being sensitive to roughness, so this texture information can be very valuable in improving the land use land cover classification accuracies. Then similar to optical data, you have flexibility of making certain indices. For example, NDVI indices you are familiar with. Similarly, here also you can use different polarization channels, and you can make index like radar fractional density index, where HS and HV polarizations are used. And this index is sensitive to the structural changes in forest areas, and this can highlight the areas which have been disturbed, or the areas which are intact. So RFDI is a one such index, and there are other indexes also available, based which you can compute based on SAR data, and you can develop newer applications for forest disturbance, or even for RFDI like indices can be even can be related to biomass mapping applications. Now, these earlier example which I have shown are related to classification. Now, if you have to do quantification, for example, of parameter like forest height estimation, forest biomass estimation, carbon stock estimation, so you should have little bit idea about how the field inventory of these parameter is done. And for that you have to plan the field inventories following a sampling design. And I have given the formulas here, how above ground biomass is computed at plot level. So you can refer to these formulas, and how carbon stock is determined for a particular sample plot. Once you have a sufficient statistically sound sampling design, and you have laid out sufficient number of sample plots in an area, then this data you can use for further modeling and further integration with SAR data. Now, when it comes to forest height estimation, so there are two things. One is tree height estimation, and another is forest canopy height estimation. At present, we are mainly doing the forest canopy height estimation using SAR data. And height is a very important parameter for estimating volume, biomass, productivity. And there could be different approaches for height estimation using SAR data. As you are aware that there is one example, for instance, you have the SARTM data, which is which gives you digital elevation model. But over forest areas, this is a DSM model, DSM, digital surface model. So if you have a digital elevation model, terrain model for particular area, so you can use this DSM and you can subtract the terrain from that, and then you can get a effective canopy height. So this could be one approach. Another approach could be that you use a longer wavelength, P band, which can penetrate up to the ground, and another you can use the smaller wavelengths like X band, which scatters from the top of the canopy. And these differences in the scattering properties of these two wavelengths can again be used for deriving the forest height. Other important, which is important technique, is the forest INSAR based inversion techniques. Now here we are exploring the application of polarimetric interferometric SAR for height estimation. Here, basically, two things are there. One is polarimetry. Polarimetry is used basically to differentiate different types of target, like forest, and there is a ground associated with that. While interferometry is used for location of scattering phase center or deriving the height information. So this way, polarimetry is very effective over interferometry in estimating the forest height. Uh, Although one single baseline Polinsar data is sufficient, but what we do while estimating the forest canopy height, we use multiple Polinsar acquisitions to obtain a good performance of the inversion model. So in this example, you can see that the based on Polinsar data, the forest height map of an area has been derived, and similarly, these forest multiple Polinsar in observations can also be used for forest canopy profiling, and this profile, based on this profile, you can get an idea that what kind of forest it is. So forest canopies roughness changes with respect to disturbance, with respect to their age. So this type of profiling of forest canopy can help in understanding the structural changes. Uh, Another thing is height, structure of the forest. Height is one parameter which directly goes into the biomass modeling, but structure information is also very important. How canopy looks like, how are different layers, how many layers of vegetations are there in the forest. For that purpose, SAR tomography is being used, and here basically it not only gives information about the ground topography but also the different structural element in the forest canopy, for example the large branches, medium branches, and small branches. And so here the thing is that you need multiple passes over the forest canopy at different angles, and such type of experimentation has been extensively demonstrated using airborne platform, where it is very where it is easier as compared to the satellite based observation to procure data with equidistance separations. And this type of data can be very useful. Again, you can see here the tomographic profile of a temperate forest, where you can see that the bottom of the tree base, you have a different scattering, double bounce scattering, then you have the volume scattering over tree areas. So this way, SAR tomography can help in preparing the 3D or 3D construction of the forest canopy. And this has a lot of applications linked to this in forestry. If you know the structure of the forest, you can relate it to many other functions of the forest. Then finally, the biomass estimation is a very important application, as I told. Here also we have different approaches. We have empirical, semi-empirical, and inversion approaches. The most straightforward approach is that you generate backscatter images and you relate it with the plot data, biomass plot data, and enough literature is available about the sensitivity of different wavelengths to biomass, C band, L band, P band. Another thing is that you can derive a coherence image from interferometric pair, and this coherence is inversely related to the biomass. If there is a higher biomass, so then there is a lower coherence, and this relationship can be potentially used for deriving the biomass. But the important thing is that if you want to use the polarimetric interferometric SAR data, then there are certain empirical model like water cloud model and random volume over ground methods. So these models actually require a high quality data with the proper configuration, and this type of models can simulate a very high quantity of forest biomass, and that's why there is a lot of emphasis on development of the physical inversion model for forest biomass estimations. And this is one example where water cloud model has been used for estimating the above ground biomass of a forest. So basically, the currently we have a lot of understanding about the SAR and newer technique like tomography and from the airborne experiments, and we want to replicate such application from the space-bound platform also. But at present we have mostly the data which is very good for doing application like pollen SAR application and tomographic application is being done through TerraSAR tandem data. And whereas the other missions are also available radar set 2 allows to which are offering very high quality polarimetric data for forestry applications, but the cost is very high. Data is not freely available. These are the currently the major challenges. Also, SAR data processing is relatively complex. One is because of the large volume of the data, and also you need appropriate models to process it. And then we have mm, other kind of challenges in forestry that although you can have the forest height information derived from SAR data, but height and biomass they differ, relationship differ from place to place. So model derived from one area cannot be straightforward applied to the other area, other distinct ecological zone. Then we have in future a lot of data coming from in polarimetric data coming from missions like NISAR missions around 2022 or 23 time period. We will have very good data from NISAR, from biomass mission which is planned by ESA, European Space Agencies, and other countries also like Tandem L proposed by DLR and JAXA. So this is the very good time that one should if one should uh, go for understanding and in-depth understanding of these techniques, particularly in forestry field. And also there will be possibility that these missions will be providing the products. The first time we will be getting products, just like I showed one product on forest cover chain detection using SAR data. And by 2020-23 time frame, the agencies, space agencies are also targeting for providing space-based forest biomass and biomass change product. So with this, I will end my presentation here. I have given basically an overview of various applications which are available here for from polarimetric SAR data processing. Thank you all.